Okay, without further ado, I'm going to hand this over to Dr. Peter Wright, who will tell us about vaccine development for COVID-19.
Great. Thank you, David. This has been an area of interest for me. Vaccines, literally all of my professional career. There's hardly a vaccine that I haven't touched or tested at some point during its preclinical and clinical development. So the questions that come up around a vaccine for COVID-19 are really very interesting to me, and ones that I would like to address with you. And I'm going to bring up some of the concerns I have, because developing vaccines are not easy. And there have been missteps with other vaccines, conceivably will be with this, but it does represent, I think, in everybody's viewpoint, sort of the ultimate solution to control of this epidemic. So maybe if we can have the next slide. I really have no conflicts of interest. I am leading with David and a couple of others a consortium at Dartmouth and DHMC to define the immune responses to COVID-19 infection, which has internal DHMC and NIH funding. It's not specifically around the development of vaccines, and if people have questions about what we're trying to do and how we're approaching it, it's something that we could take up in the question session. If we could have the next slide. I think I'm not going to try to spend a lot of time with the history of vaccines. They've been listed as one of the primary advances in healthcare and its delivery, certainly for the last century. But I've taken on, along obviously with many others, a couple of very tough pathogens to develop vaccines for, and maybe they have taught us as much as some of our successes around what to anticipate with the COVID vaccine. And those include vaccines for AIDS and vaccines for respiratory syncytial virus, a pediatric disease. And some of the lessons that I've sort of drawn out of all of this are that understanding structure of the virus is critical, and there we're well ahead of the game, as I'll show you with COVID-19. I think it's important to realize that vaccines can and have caused enhanced disease, and measles and particularly respiratory syncytial virus stand out as vaccines which in their development had iterations that in fact caused either enhanced or atypical disease. So that's a word of caution, and something that all of us who are in the development of vaccines keep very much in mind. I think it's really important to understand the immune response, and the SARS-CoV-2 virus is proving to be really interesting and complex in that regard. And I think you've all heard and been exposed to the fact that it seems likely that a significant part of the illness, or at least a phase of the illness in COVID-19, may be induced by immunity, and that obviously is a cause for concern. And that's one of the things in this overarching consortium that we put together that we're looking quite hard at. But a comment would be that where it's been seen with viral vaccines, it's been seen with whole virus inactivated vaccines. And obviously we have vaccines like influenza vaccine that are exactly in that category and don't cause enhanced disease. But for many others, we really have to understand the immune response. And in the broadest sense, you can divide that into what happens with serum antibody, what happens at the mucosal surface with mucosal antibodies. And for a virus, it's a respiratory virus, you would want very much to keep that in mind. You have B-cell immunity, which is what we think of perhaps first, antibody, but you also have cell-mediated immunity. Still, in spite of a great deal of effort, much less well understood, but potentially very important in terms of the immune response. So the development of vaccines for coronaviruses has gone very quickly, and part of it has been based on the fact that people had already been considering and studying other coronaviruses, SARS and MERS, and even the sort of garden variety of coronaviruses that infect people in childhood, and even had done some structural work on what the protein, the key protein in the coronaviruses, the spike protein, looked like. So I think you have prepared investigators, many of whom have blunted their swords on HIV vaccines. There has been funding available for all stages of vaccine development. And so perhaps we have some capacity to operate at Operation Warp Speed, as President Trump has referred to it. But let's be cautious as we move forward. So if we can have the next slide. There are many steps in vaccine development, and these are really only a few of them. The conceptualization, the ability to grow, to replicate, to study the structure of a virus. One can then proceed to animal studies, and in some cases they are very useful. In some cases, they perhaps are not as useful as you might think. And then you have phase 1 and 2 studies. These are in humans, designed primarily to look at safety. So the first reported outcome is always safety, but it also gives you a hint about immunogenicity. So these are studies that may involve as few as 10, and in phase 2, somewhere in the low 100s, very carefully studied vaccines, and we are with several vaccines in this phase now. You have phase 3, which are studies in which large numbers of people are given a vaccine with a hope for proving that a vaccine works, that they will be exposed to the vaccine, exposed to the virus, and you'll have a measure of whether or not they become ill. These are studies that can take a particularly long time, and we'll talk about one way that one might get around that in just a few minutes. But at the same time, you have regulatory and manufacturing considerations. And then there are real considerations about what is the equitable distribution of a vaccine. because this is not an infection and the illness is occurring only in the United States, but it's already, as you're well aware, a global pandemic. And so the utilization and availability of vaccines in parts of the developing world are one of the things that's always concerned me and concerns certain groups of individuals who've really thought about this. We can have the next slide. We now turn to the coronavirus, and specifically to the spike protein, as it's called. And even more specifically, I don't know that you can see my marker or not, my guide to the green RBD, or receptor binding domain. This is the area of the coronavirus spike protein that interacts with the ACE2 receptor that binds the virus to the cells lining the respiratory tract and enables the virus to get in. And we already know from other viruses, other coronaviruses and vaccines, that this is the logical target for a vaccine that incorporates somehow the spike structure, but maybe even more specifically is aimed at presenting the receptor binding domain. And it can be, it's further complicated by the fact that the spike protein can change its conformation as it attaches to a cell, and some of the epitopes may be best recognized, some of the antibodies may best recognize the virus in its pre-fusion and some in its post-fusion state. And so you're looking in phase 1 and phase 2 studies, and then looking at the antibody that's generated after that, at how these antibodies are reacting with this receptor binding domain. So this is, one hand, this is very much a reductionist approach to developing a vaccine, because if this is a receptor binding domain, there's a whole basketball or maybe considerably bigger that represents the whole virus, that has many different proteins, some of which actually aren't incorporated into the virus as it's released, but are coded for in the virus, play a role in the virus replication. And any of them theoretically could be a target for a vaccine, but everybody is focusing on the spike protein and particularly on this receptor binding domain. We can have the next slide. There are several candidates that appear to be leading candidates, but the technology that's being used to develop these vaccines has not yet led to a successful licensed vaccine. So we're very much not only in choosing a very limited portion of the virus as our target, but in choosing the methodology to be used, we're dealing with things that are cutting edge, so to speak. So RNA vaccines are being developed in London at Imperial College and in Bethesda, Maryland, at the Vaccine Research Center. This is a really interesting concept of delivering messenger RNA to the cell and having that then be replicated to form viral proteins or protein, which in turn are recognized by the immune system. Another approach that came out of HIV work was to take an adenovirus originally identified in chimpanzees and basically non-replicating in humans. And again, developing this as a vaccine that really is dependent on injection and not on replication, either of the vector, in this case, chimp adenovirus, which has had the coronavirus spike protein pasted into it, or in the RNA vaccines. Neither of them replicated in the human. So one would think they would be, and so far they have proven to be, very safe vaccines. But I think it's fair to say, puzzle to me certainly, is how the RNA can get into enough cells, literally sort of being pierced by the end of the needle as you give an injection, or infected by this non-replicating vector, which has got one single cycle to go through, and yet stimulate a vigorous immune response. But to date, in the phase 1 and phase 2 studies, both of these vaccines appear to be doing quite well. So we can have the next slide. So here we come back to animal studies, and sort of the higher the animal is, the more relevant it may be to what will happen in humans. And it's reported, although not yet published to my knowledge, that animals, rhesus macaques, were given the Oxford vaccine, the chimp adenovirus vaccine, and then were challenged with COVID-19 and were protected. So that's a very important sort of first critical step to thinking that, at least with this vaccine, that the group in Oxford may be on the right track. We can have the next slide. I've had a long-standing interest in mucosal antibody, and these are some of the antibody responses that have been seen in COVID-infected volunteers that we have studied to date. And COVID-infected and uninfected controls. So the uninfected controls are shown in red, and you can see very much of their antibodies are at the lower end of the scale, or low level of both quantity and potentially potency. On the other hand, the green, particularly the nasal IgA, in the people who've been infected 1 month after they've been infected, show very considerable levels of antibody. This is not binding, this is binding antibody, not neutralizing antibody, a difference that I think is important in the ultimate interpretation of how a vaccine will work. So this is after natural infection. It's another benchmark that you'll look at for vaccines, and you'll say, does a vaccine, particularly one given intramuscularly, stimulate this local response, which you would think would be very important for control of a virus that replicates in the respiratory tract. If we can have the next slide. Running over a little bit, but we'll be done shortly. These are studies that we did with polio, another mucosal vaccine, in this case, the respiratory tract. And so we looked in the stool at the recovery of virus and its correlation with the presence of mucosal IgA and what vaccine they got. So the group in the center, partially bracketed by the red line, got TOPV. So to type 2, they had received an OPV vaccine, the live Sabin vaccine, and they had very, very little virus shedding. On the other hand, if they had gotten some Sabin vaccine, but not including the type 2 and inactivated vaccine, so that they had good serum antibodies to polio, they still had to develop no mucosal antibody, and they shed lots of virus. So if you can follow that rationale, you come to the conclusion that for protection against COVID-19 and for determining the risk of reinfection, it may be very important to look at antibody in the respiratory tract. We can have the next slide. This is, I think, a very controversial area, and I will go out on a limb and I will say that I think it is quite likely that we will expose a small group of young adults, highly informed and monitored, challenged with a low dose of SARS-CoV-2 after they have been vaccinated, and hope that, like the rhesus monkey, we can demonstrate that they are protected. The alternative, which I have discussed, is that we will have to vaccinate a large number of people without knowing whether the vaccine works, and wait for them to receive a natural challenge. This potentially puts more people at risk if there's a substantial recurrence of vaccine in the fall. But I have to say that we cannot yet predict what causes severe illness and death, and that we have enhanced disease with vaccine. And if either of these happened in the context of a trial, obviously we'd be back to square one, and any predictions about when we will get a vaccine would have to be completely revised. So we can have the next slide. So developing vaccines is a complicated business. There are academic institutions, there are governmental institutions, the Vaccine Research Center that I mentioned at NIH. There are small biotech companies that often have good ideas, and often then in turn are swallowed up by large multinational drug companies, of which there are a half dozen around the world that really end up providing much of the vaccines. There are groups that go by various acronyms: a Global Alliance for Vaccine Introduction or something like that, CEPI, which is the Center for, Center for Availability of Vaccines on a global basis. I think Bill Gates deserves special mention here. My understanding is that he has taken his efforts and funding in this particular area towards making sure that there's capacity to manufacture vaccines when we do get one. So a lot of efforts are going on with vaccines. You can have, I think, what is probably the final slide. This is a question of how long it will take. If everything worked right, and I just have to say it hardly ever does, we could have a vaccine by the end of the year or early next year. And because people like Bill Gates are concerned about manufacturing capacity, many of the downstream issues are being addressed. A failed trial or worse enhancement of disease would put us back in a much, much longer timeline and force us to go back and fully dissect and understand the immunopathogenesis of this disease. Other risks include this virus may change, and indeed there's a suggestion that the virus originally in China and the virus that's now circulating in the United States has undergone both genetic change and to an extent antigenic change. So it's a partially new environment, a new virus, and you may have to remake the vaccine to take advantage of this, and the vaccine in turn, if flu would be any kind of an example, will continue to mutate and change. And I think, and this is my own bias really, that mucosal immunity may be critical for vaccine efficacy. And I'm not sure the current vaccines given intramuscularly will induce this. I don't know how to do it, but I just have to pose that as a question. Let's see if there's one more slide. A nice review, particularly aimed at the idea of enhancement of disease, has just been published in the last couple of days by Dr. Graham at NIH in the Vaccine Research Center. And he covers some of the points that I've been making. And so with that, I will stop, and I apologize for running over a bit, but I hope this stimulates some questions and comments.
Thank you so much, Peter. That was fantastic, and I'm sure people are glad that you ran over a little bit to convey all of this.